Okay, thank you, Chairman. So, good afternoon, everybody. My name is Young-Sang Kim from Jeonnam National University of South Korea. So, actually, I'm very about my topics today because, as you heard about from our previous two professors, so actually, I'm not familiar with that disaster management because I'm not social department. So, actually, I'm engineering, geotechnical engineering. So I have been in Japan 2 years from 2000 to 2002 in Kyoto University, the Disaster Prevention Institute. Actually, in Korea, fortunately, we have very rare disaster. I think that students may have ideas about the disaster in Korea. Actually, we have a flood and a typhoon are the major topics of the disasters. We have rare earthquakes. Recently, we have 2 earthquakes. So we have almost started to study about the topic related with earthquake. As like that, I think that disaster prevention and mitigation might be very low, very difficult for me. So I, by myself, decided to introduce just one technical solution, not solutions, maybe the suggestion about for the protecting and monitoring the geo-disaster, one of the geo-disaster by FEG sensors. This is just a technical suggestion to you. So this is my contents, background, and then I will introduce you FEG sensors embedded TENDON. It's quite strange to you, maybe. So I will explain you about the concept, and then I will show you some applications, and then development of monitoring systems using FEG sensor embedded TENDON. And I will conclude. So actually, as you know, whole world is suffering from intensive rainfalls due to the global climate changes. So actually, you can see there's 3 figures. That the one is the figure taken after the failure of a railway. During the construction, there was a big the slope stability failures. So actually, width is 45 meters and height is 15 meters. So under the construction, even though we reinforced, it is the slope failure occurred during the construction due to the heavy rains after a few days. And also this figure shows you slope failures at the road after rainfall. And also this is, you can see the cracks occurred at the retaining wall behind the residential areas. So all the slope is very risky areas for the geotechnical engineers against geo-disaster. So we have to make a proper reinforcement and the monitoring system for these systems. One of the popular reinforcement for the retaining wall is ground anchors. This is a head. Ground anchor is composed of 3 parts. One is the head, and then free length and the fixed length. So this is a PC strand. I will show you the figures later. And then we make a drills as like this, make a drill holes, and then put the PC strand inside, and they give a grout. This may mixed kind of a cement. So, and then we pull out and fixed at the wall like that. Then maybe it can give the pre-stress, a kind of a compression to the ground. So this wall can resist against the overturning of the ground, even after the rain falls or something. So, however, even though we gave the pre-stress to the ground anchors, there is just some failure mode like this, tensile failure of the tendon, and the pull out, and then pull out of all the tension and grout bond, and sometimes it's bended, and then toe will be translated like this. This kind of failure mode, we cannot monitor, or even we cannot expect. So monitoring and warning system for this kind of failure mode is required. So now, we have two kinds of systems for measuring the safety of the returning structures. One is the external measuring systems. We put the load cell in front of the head like this. And then sometimes we have put this vibrating wire strain gauge systems into the hole like that. Or recently we developed the Transmech systems. And this kind of old systems are electromechanical sensors. So, however, these sensors are suffering from noise during long-distance transmissions, and they have immunity to electromagnetic interference. So, I would like to say that we have to develop a new monitoring system for long stability for the ground anchors. So, I would like to introduce one suggestion for using the fiber brake grading sensors for embedded tendon. So as you see here, this figure shows you a fiber optic. So this is very small in dimension, almost 0.3 millimeters. And then the fiber brake grading is a fiber optic passive component exhibiting basic functional attribute for reflecting and filtering the waves. And this very FPGA are relatively simple to manufacture and small in dimension, as I said, and low cost. So it has been used as a telecommunication areas and as well as sensors. We can use these sensors as strain sensors or temperature sensors, chemical sensors, and even accelerometers. You see here, FVG is a longitudinal periodic variation of the index of the refraction in the core. So fiber optics is composed of the core and cladding covered with the cover and the coating. Then we make a brake grating like this with a UV light. And then if we enter the signals into the core, then the spacing of the variation is determined. This variation, spacing is determined by the wavelengths of the light to be reflected. So it means that if we input a signal into the core, then the specific refract signals comes out, and then others will be transmitted. Now, after the temperatures and strain changes, then this spacing of the brake grating will be changed. Then the shifted or this spacing make the refracted signals change after changing the temperatures and strains. So with the temperature changes or strain changes, as I said, the resonance wavelengths will be changed like this. So by measuring the shift of the wavelengths, we can measure sometimes the strains, and sometimes we can measure the way the temperature changes. This is I developed a basic concept of the FPGA sensor embedded tendon. I put these sensors into the center of the 7-wire strand. This is, I think that you may know this strand. So this is a kind of steel wires, which is used for the civil engineering department. Well, so this it has a straight the king cables and then 6 cables twisted around the center cables. Then actually, I would like to make a hole inside of the king cables. It was very difficult for us to make a hole inside. So actually, we made an idea that replace the center cables. So I will show you the process to make these cables. Anyway, after replacing the center cables with the tube type cables, and then insert the optical fiber sensor with the brake sensors, and then fixed with a specialized designed resin. Now this is the test result. I confirm whether the sensor works well. This is a load cell outside, and the sensor strain gauge sensors very close to the FE sensors. And you look at here, by changing the load, the load measured from the FE sensors matches with the load cell and strain gauges. So tensile force from the FE sensors may represent the force such as the load cell and the strain gauges. And I think that I have only 15 minutes, right? So I think that I passed this. So actually, as I said, the FV sensors is sensitive to the strains and the temperatures. But as I said, I explained, I will use this sensor inside of the ground. So actually, about 5 meters depth, there is a little temperature changes. So I think we can, conclusively, I think we can neglect the temperature changes for the checking or determine the strains from the FV sensors. From the lab test, we determine the temperature sensitivity coefficient. And then this is a test we measured, measuring the temperatures on the ground. So we measured for 1 month with the FV sensors and compare with the result thermometers from the Korea Meteorological Agency. And we found that at 3.5 meters from the ground matches well the temperatures from the FV sensors and then thermometers from the Korea Meteorological Agency. However, you can see, as I said, below the 7.3 meters depth, there is a little temperature changes. So, as I said, there is no change in temperatures below 5 meters. So I explained the dimensions of the tension type here. So I put the FV sensors at here, pre-length areas. So as I said, we pull out the PC strain and fix it at the wall like that. So about 100 kilonewtons per ground anchors usually. So if the fixed ground moves, the tension force will be decreased. Or sometimes this movement to lose all pre-stressing force. So I suggest use this system to measure or monitor after reinforcing the retaining wall about the changing in the tension force using the FVGs. So this is a manufacturing process of the FVG embedded tendon. You see, we cut a 7-wire strand as the design length for the anchors, and then dismantle the strand and then replace king cables like this, and then insert the optical fibers inside the king cables, and then fix with the resins with pumping systems, and then protecting the cap like this, and then testing the FV sensors after inserting these cables to the anchor systems. After making the one FV sensor embedded tendon, we send this system to the manufacturer of the anchors like that. Then they make that the anchor systems with our FV sensor embedded tendon. Usually 3 or 5 or 6 PC strands is used for making one anchors. So just one replacing the PC strand, we can measure the tension force changes using FVG sensors. This is an installation process. After we install, we're giving the pre-stress force, and then we measure the pre-stress force changes with the FVG sensors and then load cell for the comparison. We measure the pre-stress force changes for 1 year, from 2010 September and then 2011 September like that. This is ground temperature changes for 1 year, the seasonal changes. And then this is tension force changes during that seasons. You can see here very similar changes. It means that this FV sensors is affected by the temperature changes of the ground. So we compensated with the temperature sensitivity coefficient. So we found that this is a tension force after the compensation. And then this is a force measured by the load cell. So as you can see here, this was the original force measured from the FV sensors. But after compensation with respect to the tension temperatures. The tension force very consistent and comparable with the force measured from the load cell. And then I will show, so I will show briefly how we can use that systems to the real world. This is a steep slope continuous monitoring system using FV sensor embedded tendon. Okay. We put the FV sensor embedded tendon to the slope like that, and then we measured the groundwater tables or even rain gauges. With a measured value, we can analyze or give the, after analyzing measured data, we can give the safety criterion on the software, and we can give people the warning systems using the result from the measured result. So this is test site we do, and this is a main screen capture, so developed the systems, there's photographs, all the systems shown in the photos, and then this is a groundwater table changes and pre-stress force changes also can be seen. And then we set the alarm with safety criteria from the government. And then we can give the warning systems, the cautions, or even danger system to the people who take care of these slopes when the monitored value violates the safety criterion. So this is a conclusion. So FV sensor embedded tendon was applied to the anchors to reinforce and monitor together simultaneously the steep slope. And then these systems can show the warning message when the monitored value violates the safety criterion. So I think that this technology may help us to manage the disaster risk and eventually make a sustainable growth possible. Okay, thank you very much for your kind attention.
Thank you very much.